Hello, everybody. Welcome to my video recitation. I'm very sorry that I can't be there with you in person, but I am going to Denver tomorrow for a convention, like an academic thing. I'm pretty excited about it, to be honest, but I won't be here. And so here's the lecture. I'll try to keep it to the normal amount of time. So let me share my screen. And there are three documents that I want to go over together. I've already put the first two on Canvas. The first one is our recitation notes, so I hope everybody can see this. And the second one is the recitation additional information. We'll do that in a minute. That would normally be what I'd give you as a handout. And then we'll go through the quiz number 4. The quiz is quite straightforward this week. So the recitation notes, there are 4 kinds of probability that we're learning now. And in fact, the only ones that are on the quiz are the first one, disjoint, and the third one, independent rule. These are kind of the most basic ones and the ones that you really use the most. So that's actually very good. Now, the first one is this symbol, which looks like a U. And this U symbol over here, I can probably draw. Oh, but should I draw? What's going to happen to me if I draw? Am I going to mess up this whole thing? Okay, I'm not going to draw. I don't know what I'm doing. So this U symbol right here is the symbol for or, and that would be designated by a plus sign or addition. So when you see the U means plus. When we see the upside down U, that means and that is signifying multiplication. So these are our 2 basic symbols, the U and the upside down U. The right side up U means or, and that means addition. The upside down U, the rainbow, means and that means multiplication. Then we have these 2 other rules. This is the general addition rule, and that is where there is overlap, where there's like a Venn diagram. And I hope everybody knows what a Venn diagram is, but it's a diagram. It's a diagram that looks like this. So you have something in column A and column B. So you can see in A is one set of things, B is one set of things, and C in the middle is where they overlap. Now, let's say, for example, that A is fiction books in a library. Okay, so A over here is all the fiction books in a library. B over here are all the history books in a library. So we want to know, and of course, there's a little bit of overlap because there are some books that are fictional history, and that's the overlap. So if we wanted to know how many books are fiction or history, but not both, then we'd want to know how much is A plus B, but minus this middle part, because we don't want to know that. We'll do some examples in a minute. And that is called the general addition rule. Then we have similar thing, the general multiplication rule. This is the only other symbol that you're going to see, which is this straight line, B given that A. So now we have a third one. The straight line means given that, assuming that. So it's B, assuming that A happened. And we'll look at some examples. One other thing we need to know is how to approximate independence. And we can approximate independence if the population, N, all the books in the library, let's say there's 50,000 books in the library. Now, how big is our sample? Let's say I want to take a sample of 100 books. And there are 50,000 books in the library. Is that sample big enough so that I can use the independent rules here? Well, I'd need to know 10 times my sample size. My sample size, little n, is 100. So 10 times 100, well, that's 1,000. N, the population, 50,000 books in the library is greater than 1,000. So we could use the independent rule. Again, we'll look at some examples. Here is the example that Christina gave us. So suppose you have a box with 3,000 blue marbles, 200 red marbles, and 4,000 yellow marbles. So how many marbles total are in the box? right? That's 3,000 plus 200 plus 4,000. So that's 7,200 total. What's the probability of pulling out a red marble? Well, that's just going to be P of red. So P means probability. The probability of red is just going to be 200, because there's 200 red marbles, divided by the total number. We just said is 7,200. 200 divided by 7,200 is 0.03. That's the probability. Remember, that's the key word here, probability, not the percentage chance. The percent chance would be 3%. What is the, again, probability? So we're looking for a decimal. What's the probability of pulling out a red marble? Or, okay, so now we have our first sort of proportion question. And remember, if you go back up to the top, or is the U symbol, and it's disjointed. The probability of A or B is the probability of A plus the probability of B. So let's go back down to the question. What's the probability of pulling out a red marble or a blue marble? So we know it's going to be probability of red. We just did that here. Plus probability of blue. So probability of red plus probability of blue. Probability of red, we did. That's 200 over 7,200. Probability of blue, there are 3,000 blue marbles. So it'd be 3,000 over 7,200. So this plus this equals 44.44 because it's probability. And if we wanted a percentage, it would be 44% chance. Assuming independence, what does that mean? So this got me for a little while when I was first learning this. Independence means your first sort of experiment, you taking out a marble from this box, does not influence the second experiment. Now, if I only have 3 marbles, 1 red, 1 blue, 1 yellow, and I want, well, let's say I have like 6 marbles, 2 red, 2 blue, 2 yellow, and I take out 1 red. Now I ask you, what's the probability that I'll take out another red marble? Well, originally it was 2 out of 6. It was 1/3 because there were, 2 red, 2 blue, 2 yellow. It's a 2 out of 6 possibility that I take out a red. But if I already took out a red, what's the probability I'll pick, blind, I'll pick another red? Well, it's not 2 out of 6 anymore. Now it's 1 out of 5. So that's not independent because my first pick influenced my second pick. But like we said here, if you have a really big population, like if we had 10,000 marbles in the box and I'm just choosing 2 or 3, let's say I choose 5. So I choose 5 marbles out of 10,000. Will choosing 1 influence my next choice? Well, let's look at this equation. 10 times, I said I'm choosing 5 marbles. So 10 times 5, that's 50. There are 10,000 in the box. 10,000 is greater than 50. We can assume that the first pick doesn't influence the second pick. This is all sort of hypothetical stuff, but let's assume independence. What's the probability of pulling out a red marble? And so we see and, we know we're going to our independent rule, and means multiply. So red marble and blue marble. Red marble we know is 200 out of 7,200. Blue we know is 3,000 out of 7,200. So we have the rainbow, red and blue. That's the probability of red times the probability of blue. And that gives us 0.012 or yes, 1.2% chance of pulling out a red marble and a blue marble. So pretty low probability. That's it. That's the example Christina gave us. Okay, let's go on to the recitation notes, the examples, the additional notes, sorry, that I came up with. So I wrote the same information here at the top, the rules. I mean, I wrote them a little, my style, a little more kind of like, I don't know, lawyers like bullet points. So I wrote them with bullet points. And then I gave some examples. Now, if this would be the handout sheet if we were together, but because we're not, I put the answers down here already and we can just discuss them. Then we'll go through quiz 4. By the way, I'm going to tell you the attendance question in just a minute. But I mean, I could tell you now, but the attendance question is, in our recitation example, what are the two numbers for our dice example? And as you see here, the numbers are 2 and 5. So if you go to Canvas, I can even show you this. If you go to Canvas, to this week, and here it says asynchronous attendance, you click on that. I can preview it. You will take this, quiz, but the quiz has one question. In the recitation example regarding the probability of rolling dice, what two numbers did we use in the example? The answer is 2 and 5. Okay, that's how you get attendance for being here today with me asynchronously on Zoom. And thank you for your attendance. Okay, so let's do some disjoint examples first, where it's or. Flipping a coin. You flip a coin once. What's the probability of getting heads or tails? Now, probably that's very obvious to you. If you flip a coin, it's a 50-50 chance. But let's look at the formula. This is the U, which means or, and that is addition. The U means addition. So probability of A, which is heads, plus the probability of B. So what is the probability of getting either heads or tails? Well, it's 0.5 plus 0.5, right? A plus B. It's 1, right? You're definitely going to get, if you're flipping a coin, you're definitely going to get either heads or tails. I mean, I guess, look, there is a little possibility. Some people say if you flip a coin, it could land like on the edge. That's never happened to me, but we're going to assume that's not happening. So you got to be careful of the question. This didn't say the probability of getting heads or tails. It said either heads or tails. Next, drawing cards. From a standard deck of cards, that's 52 cards, what is the probability of drawing either a heart or a club in a single draw? So you're just drawing once from the deck. What's the probability of getting A or B? So we know this is or, we know that means addition. So we use our addition one. So the probability of a heart or a club, and we know that is the probability of heart plus the probability of club. The probability of a heart, well, there are 13 of each suit in a deck of cards. So 13 out of 52 is 0.25. Probability of a club is the same. So 0.25 plus 0.25 equals 0.5. Why aren't these like a Venn diagram? Where is there overlap? I mean, if I take a card out of the deck, doesn't that influence the deck? Well, there's another question later that kind of touches on that, because you could say if I take a heart out of a deck, then, so here's the deal. If I said in 2 draws, that would change things. Because then in the first draw, taking a heart would be 13 out of 52. But then in the second draw, if I don't put the card back in the deck, it becomes 13 out of 51 because I took a card out. So taking a card out of a deck does influence the next draw. It's not 13 out of 52 anymore. It's 13 out of 51. But that's not what I wrote. Let me change this back to the original thing. A single draw. So in one draw, it's either going to be 0.25 or 0.25. So it's a 50% chance I get either a heart or a club. One more, disjoint. When rolling a 6-sided die, what's the probability of rolling a 2 or a 5? So we have an or, and we have an either. You can see there's either in each of these. So an or, we know that's addition. What's the probability of rolling a 2? Well, the probability of rolling a 2 is 1 out of 6. It's a 6-sided die. The probability of a 5 is 1 out of 6. And we know this is addition, so it's 1/6 plus 1/6 equals 1/3. Okay, moving on to the general addition. And that is the Venn diagram that I was talking about where there is overlap. So let's assume on a survey, 40% of respondents prefer tea, 50% prefer coffee, and 10% enjoy both. What's the probability that a randomly selected respondent prefers either tea or coffee, but not both? So now what we want to know is who likes tea, who likes coffee, but not people who like both. So we can't just do tea plus coffee. We have to do tea plus coffee minus both. So, okay, that is our formula for this is the probability of A plus the probability of B minus the both part. So the probability of A and B, which is our multiplying one we'll do in a minute. So the probability of tea, the probability of coffee, the probability of tea and coffee. We don't need to do any math here really because it gave us this in the question. The probability of somebody liking tea, 40%, so 0.4. The probability of somebody liking coffee, 50%, so 0.5. And the probability of liking both, 10%, so 0.1. All we have to do is basic addition and subtraction. We get 0.4 plus 0.5 is 0.9, minus 0.1 is 0.8. So 80% of people like coffee or tea, but not both. Next, same style, the general addition rule. In a library, here's the example I was talking about before. In a library, 30% of readers prefer fiction, 20% prefer nonfiction, and 5% like both. So again, we already have the numbers. What is the probability that a randomly chosen person likes either fiction or nonfiction, but not both? Okay, so we want to know fiction and nonfiction, but not both. So we're going to have to do, A plus B minus C, minus the and part. So we have probability of fiction, it says, is 0.3, 30%. Probability of nonfiction, it says, is 0.2. And the probability of both, it says, is 5%, 0.05. So we just do the basic math. We get 0.45, or 45% of people like fiction or nonfiction, but not both. Last one for general addition rule, this overlap. In a neighborhood, 60% of households have dogs, 30% have cats, and 15% have both. What is the probability that a randomly selected household has either a dog or a cat, but not both? So I hope you're getting it. I mean, this stuff drove me crazy at the beginning, but after a while, there aren't that many combinations in probability. So what's the probability that they have dogs? It says 60%, so that's 0.6. What's the probability they have cats? 30%, so 0.3. And what's the probability they have both? 15%, so 0.15. Just 0.6 plus 0.3 minus 0.15. 75% of these homes have a dog or a cat, but not both. Okay, next rule, the independent rule. This is our and, so our multiplication. And it's the rainbow. A rainbow B is A times B. I don't know if it's actually called rainbow. I kind of think my teacher called it that when I first learned it, but I'm not sure. Flipping 2 coins. So now you flip 2 coins. What's the probability? So flip one, flip another. What's the probability that the first coin lands heads and the second lands on tails? Well, is this independent? I have 2 separate coins. If I flip this coin, does that influence this coin at all? No. In fact, I could do it with 1 coin twice. If I flip this 1 coin and it comes up heads and I pick it up, does that influence whether it'll come up tails next? No, it's still 50-50. So we're going to use and. So that is the probability of coming up heads is 0.5, tails is 0.5. We multiply them. The probability that the first coin is heads, the second coin is tails, or the first time is heads, the second time is tails, is 0.25 or 25%. Another independent rule example. If you draw 2 cards from 2 separate decks of cards. So remember, if I'm drawing a card from deck A, that doesn't influence deck B at all. They're totally independent. So what is the probability that the first is an ace and the second is a king? Okay, so how many aces are there? There are 4 aces out of 52 cards. So the probability of an ace is 4 out of 52. How many kings are there? 4 out of 52. So both of these are 1 out of 13 or 0.077. We want to multiply those together. We get 0.0059, or there is a 0.59% chance. Very, very low percentage. If any of you are professional poker players, which I am not, maybe you knew that. One more independent rule. If the probability of hitting a green light at the first intersection is 0.5, and at the second intersection is 0.4, what is the probability of hitting green lights at both intersections, assuming each light is independent of the other? This is the question that would have killed me before I ever studied statistics. It's just so like scary, but there are keywords we're looking for. And one of the big keywords is independent. So we're talking about the probability of A, which is hitting a green light at the first intersection, and we know that's 0.5, and the probability of B, which is the second, getting a green light at the second intersection, we know that's 0.4, and we know they're independent. So we just use our independent rule. The probability of A times the probability of B. We know that's 0.5 times 0.4, we get 0.2. So it's actually not that complicated. Okay, the last one is admittedly the most complicated, the general multiplication rule, where it's not independent. So here we know that, so this rule for the general multiplication rule, now this is, we know our multiplication rule, we already saw that, A rainbow B, or A and B, I don't know if there's a special word for this, the probability of A, but here we're using a conditional. This is the third symbol you're going to see is this straight line. So the probability of B given that A, that's how I was taught to say it. The probability of B given A. The probability of B assuming that A happens. And that, we won't always need to do this math, but if we do, it's the probability of A union B. Maybe that's, well, I don't know. The probability of A multiplied by B divided by the probability of A. So let's look at three, I think I put 2 examples. So now you're going to draw 2 cards from a standard deck of 52 without replacement. So like I said, if you take 1 card out, now there's only 51. So it changes things. There is not independence. The first draw of the card does influence the second draw. So what's the probability? The first card is a heart and the second card is a diamond. So what's the probability that the first card is a heart and the second card is a diamond? So the first card is a heart. That's our event A. And we know the probability that the first card is a heart is 13 out of 52. There are 13 hearts out of 52 cards. But what about the probability that the second heart is a diamond, given that the first card was a heart? So that changes things. It doesn't change the number of diamonds. There's still 13 diamonds. But assuming that the first card was a heart, that means you took out a card. And so now we're multiplying this by the probability of B given A, which is 13 over 51. Let's look at another example. In a survey, 70%, blue A, nothing. In a survey, 70% of participants are women, and of those women, 60% are under 30. What is the probability that a randomly selected participant is a woman under 30? Okay, so now we have a probability. We want to know and. So we're going to do multiplication, but we have 2 different events. Probability A is that we're going to select a woman. Probability B is that assuming we selected a woman, she'll be under 30. If we just had probability B or event B be selecting someone under 30, well, then it might not be a woman. We want to know what's the probability that a randomly selected participant is a woman under 30, not just a person under 30. So this is going to be not independent. So we have probability of A, that we select a woman. We know that 70% are women, so that's 0.7. And then the probability of B given that A. So how many women are under 30? 60% are under 30 of the women, so that's 0.6. We multiply them, we get 0.42. There's a 42% chance we will choose a woman who's under 30. Okay, last part is assuming independence. This n is greater than or equal to 10 little n, that our population is greater than or equal to 10 times our sample size. So let's look at a couple examples of this. In a city of 100,000 people, a survey samples 1,000 individuals. If the probability of selecting a left-handed person is 0.1, 10%, can we assume independence? And if so, what is the probability of selecting two left-handed individuals in two separate draws? Okay, so first of all, can we assume independence? So what does that mean? Is our population big enough that one sample probably doesn't affect another sample? If we're talking about 52 cards, taking out one does affect that. If we're talking about 10,000 cards, taking out one for probability doesn't really affect taking out number two. So we have 100,000 people here. So big N, our population is 100,000. Our sample size is 1,000. So we do 10 times our sample size. 10 times 1,000 is 10,000. Well, 100,000 is much greater than that. We can assume independence. Okay. So what is the probability of selecting two left-handed individuals? So we want to know, and we want to know the probability that we choose someone left-handed and, not or, but and, we choose another person who's left-handed. We know that the probability of selecting a left-handed person is 0.1. So it's just and, it's just 0.1 times 0.1, 0.01. Another example of independence. A large factory produces 10,000 units daily. Okay, we know our population, 10,000. If a quality check samples 100 units, now we know our sample size, 100. With the probability of finding a defective unit being 0.02, what is the probability of finding one defective product in each of two independent samples of 100 units each? Okay, lots of words, but not actually that hard. So we know that our big N population size is 10,000. We know that our sample size is 100. So we do N is greater than or equal to 10N. So where N, little n is 100, 10 times 100 is 1,000. Obviously 10,000 is bigger. We can assume independence. Now we want to know the probability of finding a defective product in each of two independent samples. So sample one, what's the probability of finding a defective product? 0.02. And then sample two, what's the probability? Again, 0.02, we multiply them together. Last one, in a large library with over 50,000 books, a person checks out 5 books. Assuming the probability of choosing a science fiction book is 0.15, what is the probability that all 5 books selected are science fiction, assuming approximate independence due to the large library size? Can we assume independence? Well, is our population greater than or equal to 10 times our sample? The population is 50,000. Our sample is only 5. So is 50,000 bigger than 10 times, oh, I wrote that wrong, 10 times 5? Yes, obviously, it's much bigger. So we can assume independence. What's the probability of choosing a science fiction book? 0.15. What's the probability of choosing a science fiction book again? 0.15. What's the probability of choosing it again? 0.15. It keeps being 0.15. I'm sure at some point, if your sample size was big enough, it would influence the population, but certainly not for 5 books. So we're just talking about the basic independence rule, multiply them all, and you'll get your answer. Okay, those are the handout questions. Let us now turn to the quiz. So where to put the quiz? Ah, here it is. Okay, quiz number 4. Can I get rid of this? Hide sidebar. Yeah, there we go. Okay, so this is a lot of words, but it's not that bad. So major concerns for many topics, such as global climate change and Social Security benefits, include population growth rates and age of the population. So we pretty much know what our chart is going to be already. It's going to probably be these two: population growth rates and age of the population. The global median age, not the mean, but the median, has increased from just over 20 years in 1970 to just over 30 years in 2022. A report from Age Structure in Our World in Data looked at the relationship between the median age of a country and the natural growth rate of a country. Countries with lower median age tended to have higher population growth rates. Kind of makes sense, right? If you have countries that have lower median ages, that means there are more young people. So if there's more young people, it's probably more people who are having children. And so the growth rate might be higher. Let's look at this. As the median age of a population gets older, the growth rate goes down. Okay, so makes sense. As we should know from last week, this is a negative slope, right? It goes downward. So it's going to be a negative pretty much whatever we're talking about. And we have our regression equation here, which is 4.2464 minus 0.10808 times the median age. Which one is the y-intercept? While I drink my decaf coffee. The y-intercept. Well, when the median age is 0, then what is the natural growth rate? And of course, there is no real country where the median age is 0, right? That's, as we said in our last recitation, lots of times the y-intercept doesn't really make sense, and that's okay. So the y-intercept here is 4.2464. When the median age of a country is 0, the natural growth rate is 4.2464. You could see that by sort of bringing this line way back over here, and that's where 0 probably is, right? If this is 10, 20, 30, 0 would be around here. You go up to this line, you'd have, 4.2464. And theoretically, the line could go forever, but there's no country whose median age is 100, right? This is our range right here. We also have our S, our error, and our R squared. Okay, question 1. What is Pearson's correlation R? Okay, so what is R? If R squared is 89.89%. So that's R squared. What are we taking the square root of? Remember, we're taking the square root of the decimal, and we need to remember the negative sign. So 0.8989, what's the square root of 0.89? 0.8989. I'm doing this right, square root. I have, let's see if this is my right answer that I did. 0.948, so 0.95, and remember it's negative 0.95. Yes, that's the answer I got. So we take this, we turn the R squared into a decimal, and then we take the square root, and we remember to add the slope sign if it's negative or positive. What is the strength of this relationship? Well, 0.95. Negative 0.95. So remember, the negative or positive doesn't influence whether it's weak, moderate, or strong. Anything above 0.8 is strong, or below 0.8 is strong. So 0.95 is going to be very, very strong. Very strong relationship. Number 3, if you use the regression equation to make a prediction, what error or residual would you expect? So if you use the regression equation to make a prediction, so here's our regression equation. If we use this to make a prediction, but we don't know what we're using, if it's 30 or 40 or 10, we don't know. If we use this, what residual or error would you expect? Well, that would be this, 0.345 to 3 decimal places. That's the answer, 0.345. If it says what's the residual or error, and we're not using an actual value, it's just the S. Now let's find an actual value. So y hat, right? This is the predicted, not the actual growth rate. And we just say growth rate because that's what we're talking about in this chart. But it's the predicted versus the actual. So find the predicted y hat for median age equals 44.5. Okay, so let's put this in our equation. Median age 44.5. So what is 44.5 multiplied by 0.10808? 0.10808. I get 4.809. So 4.81. That sound right? 4.81. Oh, let's try that. Okay. So then we have 4.2464, 4.2464 minus 4.81 equals negative 0.563, negative 0.56. Is that right? Negative 0.56? Is that what I have in my notes? Yes, it is. Negative 0.56. Good. Number 5. What is the residual? Okay, so now we want to know about error. What is the residual for the above prediction? If, it says is, but I think Christina means if the actual growth rate for a median age of 44.5 is negative 1.39. Okay, so here we have our formula, right? And let me actually maybe just copy and paste this for a moment. I'll just put this in a Word file. Look at it down here. Okay, so what's the residual for the above prediction? Well, we know that to figure this out, our residual, here's the equation, equals actual y minus predicted y, which is also called y hat, the y with the little hat on it. That's the equation, actual y minus predicted y. So here it tells us if the actual y, the natural growth rate, is negative 1.39. Okay, so we have residual equals, we have negative 1.39 minus, and we just did this in the previous question, right? What is the y hat for 44.5? So we found that, and that was negative 0.56. Lots of negative signs. Negative 0.56. Okay, so what is negative 1.39 minus negative 0.56? I guess that's negative 1.39 plus 0.56, but I'll do it anyway. Negative 1.39 minus negative 0.56. Wait. Negative 1.39 minus, and then minus, maybe I need to use parentheses. Negative, that's not working for me. Negative 0.56, close parentheses. Yeah, then I get negative 0.83. That worked with parentheses. Or if I just did negative 1.39 negative plus 0.56, yeah, negative 0.83, that is the right answer. Negative 0.83. Negative 0.83. Okay, final question. Oh, no, final question of this part. There aren't that many more questions. There's only 3 more. What is the residual for the above prediction if the actual growth rate for a median age of 44 is negative 1? Oh, no, we just did that. Yeah, we just did that. Okay, that's the negative 0.83. Okay, now the last 3 questions. Now we're doing proportions. The number of first-year students who were admitted, accepted for the 2022 fall semester at Pitt, I wonder if this is real, was 4927. And then we know the number of students that were admitted to Dietrich School of Arts and Sciences, the School of Engineering, the School of Business Administration, Computing and Information, and Nursing. Okay, number 1. Or 6. If you were to choose one student at random from these first-year students, what would be the probability the student would be in Dietrich School? Okay, probability of Dietrich School. Dietrich School had 3431 people divided by 4927. What's 3431? 3431 divided by 4927, 4927. 0.696, 2 decimal places. Okay, so 0.70. Yeah, 0.70. 70% chance. Next, if you were to choose, ooh, this gets more points. If you were to choose one student at random, what's the probability that the student would be in the School of Engineering or the School of Computing and Information? Okay, so we know the or thing. That goes back to the disjoint. We did a bunch of examples of the or, which is addition. So, or probability of the School of Engineering or the School of Computing. So we know it's a plus. The School of Engineering, 661 divided by 4927. What's that? 661 divided by 4927. I have 0.134. So 0.134, and it's going to be plus. Probability of School of Computing, that's 253 students. The School of Computing, so 253 divided by 4927, 4927. I have 0.051, 0.051. Let's add those together. Plus 134. I have 0.186 if we round up. Sorry, 0.19, 0.1853. So 0.19. Yep, that's what I got, 0.19. Last question. Assuming independence. Okay, we know what this means. So assuming independence means we can do multiplication and we don't need any conditionals. So assuming independence, if you were to choose two students at random, what is the probability that one student is in the College of Business Administration and, so not or is going to be plus and is going to be multiply, and the other student is in the College of Business Administration? Okay, so both the same. How many are in the Business Administration? 402 out of 4927. And we're assuming independence. So 402 divided by 4927, 4927. I have 0.08, 0.08. Let's just multiply 0.08 times 0.08, 0064. Wait, that's not what I got. Is that right? Let me do that again. Oh, 3 decimal places. Okay, what am I doing wrong? Let me do that again. So 402 divided by 4927. Divided by 4927. I get 0.082. Maybe that was the difference, 0.082 if I'm using 3 decimal places. So let's try 0.082 times 0.082, 0.0067, and it's 3 decimal places, so it's 0.007. That is correct. That's what I got for the answer. And that's it. That's all of the questions. So again, this week, the quiz was focusing on kind of the 2 proportion examples that we need to know, the and the or, the U and the upside down U, and then also just reviewing regression equations, because we're going to come back to this throughout the semester. Okay, and just to remind everybody that the attendance question, which I put online for you all, was this question regarding the probability of rolling dice. What 2 numbers did we use in the example? And the answer is 2 and 5. I will also change my office hours. I need to check my schedule because I'll be away, but I will have office hours this week. If anybody has questions, of course, they'll be on Zoom, and I'll put the link in there. I hope you all have a great week. Thank you so much. And that's it. Take care and have a great week. Bye.